Okay, let's continue where we left off. We have all the chemical elements in. HSC works in minerals, not chemical elements, in its particle mode at least. So let's convert all these chemical elements to minerals. So we have wizards to help us do that. So let's start the wizard. However, because this is our example and because we can be a bit naughty, I'm going to estimate these missing values and then we're going to do this. Just to make a point when we're busy with this element to mineral wizard using HSC Geo. Okay, we have here on the bottom left our minerals that we said might be present. I'm going to put all of them in the mix. We are going to consider all the chemical elements. I'm going to put all of them in the mix as well. And we can choose what method we use. We can have least squares, non-negative least squares, or we can give weighting and give more weighting to certain chemical elements than others, or certain minerals than others. For now, let's use the default and press the calculate button. There we go. We have here that all our chemical totals are basically 105%, except one, which is 100%, but contains minus 10% dolomite. Well, no, that's not clever, is it? In fact, all the dolomite's minus. We now have to decide, because magnesium can come from talc or it can come from dolomite. And in this case, the computer program clearly said all Mg must come from talc first and then from dolomite, and it doesn't work. Could have just said 0, but it didn't. Similarly, calcite, everything seems fine. But if we now look at hematite and goethite, 1/3 hematite and magnetite, 1/3 goethite, roughly. All of them look the same for the concentrate, 17, 16, and 15, 1/3 each. So I'm going to remove dolomite as a possible mineral species. Let's have a look at what happens when we do that. So we go back to rules. Dolomite, you disappear, please. Calculate. It's as simple as that. My chemical total is still 105, and this one that was 100 is now 102. I am not very happy with magnetite, hematite, and goethite at 1/3 each. So I can, using another method, use them to calculate differently. Just for fun, why don't we use the non-negative one? Boom, I have 100% in all samples. And let's have a look. It's now all magnetite and 0 goethite. Well, what do you mean? How did you do that? Aha, you see? Different method. Why don't we put dolomite back in the mix? Because I want to see what happens when we do everything. Calculate using this method. So now it still says I have no goethite, no hematite. It can only be magnetite and talc. But in some cases there could be some dolomite, and in other cases there's not. And there's no calcite here because calcium comes from the dolomite, etc. This is really useful. So this could be a very nice method to use. Let's go back and see. It's the non-negative least squares option. However, don't accept that this will always be correct, because it will not. But there you go. I actually like this value. The results are not all exactly 100%. I like these ones slightly less than 100 because they coincide to this data in Excel, saying that there's a little bit of other stuff there as well, which is pretty normal. But this result also said that silicates are more prevalent than carbonates. So talc is probably more prevalent in sample H than dolomite. Okay? So I keep checking between these things and does it make sense or not. We're going to accept this result and just remember we used non-negative least squares just for fun. We're done. Update and close. Now, since we did it for all the streams, we now have minerals for all the streams. which may be a good idea or not, based on we never even analyzed these streams. Here's a button called Show SG. So if we scroll to the right, we have the SG for each of these streams, which is pretty cool. You can make a guess whether gravity separation will work on this or not as a stream, not as a mineral by mineral. Okay, we're done. This is mass balancing all done. I'm going to save this to the flow sheet and close it, and then I'm going to do something very important, which is save the whole process. In the next video, we're going to go and do the model fit for the kinetic behavior for each mineral particle in this cited test for flotation. And then the last video, we will model this in an operating plant. Stand by.